Today, we want to talk about the technique of trigonometric substitution. Now, this, as advertised, it is just a substitution technique, but kind of a strange substitution technique. So that's why it gets its own category. The idea behind substitution is the same as the idea behind every substitution. We're trying to integrate some function of x. And then this is not working for us. So we trade our variables. We do some kind of substitution. And get a new set of variables. Since we're talking about trigonometric substitution, let's do the recap in theta. So we do some kind of substitution to get this new integral that we know how to integrate. The point is that when we substitute into this new integral, we know how to integrate this one. And this is the environment in which we integrate. And then we have an antiderivative in theta that we don't want. So we undo the substitution that we led with to get back to our function in x, or our antiderivative in x. This is an important framework that we use all of the time. We're faced with one problem, we transform it into a problem that we know how to deal with the problem, and then go back, and then try to find all the situations where we can do this. When can we shift over, do something that we know how to do, and then shift back? How can we take what we already know and apply it to the new thing that's come along? That's like the point of this entire endeavor. How do we take what we know and apply it to the new problem that comes along? How do we take what we know and apply it to a new problem that comes along? How can we translate between these two problems? So the important aspect of a substitution is that this integral of g of theta to theta is the one we know, which substitute the goal is to get to an integral that we know how to do. The kind of messed up thing about learning about trigonometric substitution is that the goal is to get to an integral that we know how to do, and we're not going to know how to do these integrals initially. We're going to have to come up with a way to get through these integrals. But the point is, take something that we know and apply it to a new problem that comes along. Excuse me. So, what is trigonometric substitution good for? We know that regular substitution is for antiderivatives that were found using the chain rule. So what's trigonometric substitution for? Trigonometric substitution is for integrals that have some kind of x squared plus or minus a squared. I'm going to write three separate cases. I'm not going to write them in this order. Trigonometric substitution is a technique that we can apply to things with quadratic forms. and x squared plus a squared minus x squared, and x squared minus a squared. These are the signifiers of a trigonometric substitution. So trigonometric substitution is for integrals with quadratic forms. Now, we're going to focus on x squared plus or minus a squared and a squared minus x squared. We're going to focus on those, but even if there is an x term, just like we saw on Monday, we can use completing the square to write all of our quadratics in this form. We can always get to this form if we want to. So the key thing here is we're looking for quadratic forms. Trigonometric substitution is for integrating when there's quadratic stuff. Our plan follows the 3 steps that we have in this diagram. First, we need to learn how to do the substitution. We need to learn the trigonometric substitution. We need to learn the integrals that are going to be produced by trigonometric substitution. Then we also need to learn how to undo the substitution. So we've got 3 things that we need to go over. How to get to the theta integral, how to integrate the results of that substitution, and then how to undo the substitution. That's kind of the new one on us, because in original integration by substitution, undoing the substitution was really simple. In the beginning, we said w is equal to x squared. So to undo that, we just replace all the w's with x squareds. We started off by replacing the x squareds with w's, and then we just have to replace the w's with x squareds. Very simple. It's more involved in trigonometric substitution because our substitution is going to be kind of jacked up. But those are the 3 parts. Learn the substitution, learn to integrate the results of that substitution, and then learn how to undo the substitution. 3 things. 3 things that we need to learn. First, we're going to learn the substitutions. Next, we need to learn the integrals. And then we'll need to learn to undo the substitution. Those are the 3 things. Normally this takes a day, but because it's me, it takes like 3. But that's only because I actually want you to be able to do things. So that's my fatal flaw as an instructor. A quick note. We're going to learn the substitutions first, but that's going to lead us to learning these integrals. Now, the goal in the substitution is to get to an integral that you know, and we are not going to know these integrals. So in a trigonometric substitution, this theta integral, the theta integral, will be a product of powers of trig functions that is not a substitution. So the theta integral the form of the theta integral will be a product of powers of trig functions that is not substitution? So that theta integral will be a product of powers of trig functions that is not a substitution. This is why we've been spending time this week trying to figure out which products of powers of trig functions we can use substitution on and which ones we can't. That's the more important question. We have a product of powers of trig function that is not a substitution. We need to learn how to deal with that. All right, let's learn the substitution. There are three cases that we need to learn, outlined up here. A squared plus or minus x squared and x squared minus a squared. The first one is the tangent case. The tangent case is the form a squared plus x squared. If we have an a squared plus x squared, the substitution that we make is x equals a tangent of theta. Notice that we're coming at our substitution from a different direction. In integration by substitution, in the beginning, we said w is some combination of x's. W is some function of x's. Here, we're going to be replacing the x's with some expression in theta. So we're coming at substitution from the other direction. All the other rules still apply. If I make the substitution x is equal to a times the tangent of theta, then dx is a times secant squared theta d theta. Because just like all substitutions, all the x's have to become thetas. The other thing that we're going to need here, that's the addition to the trigonometric part of the substitution, is that we're going to need a Pythagorean identity. So we're looking at a squared plus x squared. The identity that we're going to need is that 1 plus tangent squared is secant squared. So we're also going to need our Pythagorean identities. Let's look at an example just of this tangent case. So what we're going to be looking for is an a squared plus x squared, and let's make our substitutions to see what happens. So here's an example of the thing we're talking about. We have an integral of square root of 9 plus x squared. We see that quadratic part, the 9 plus x squared, and we identify it as a tangent case. If the x squared is positive and the a squared is also positive. So tangent case. We can't just integrate this as it stands because of the stupid square roots. Now, if there was an x out in front, then I'd be able to do a regular substitution. Everything would be cool. Or if even there was an x cubed out in front, then I could do a regular substitution. Everything would be cool. But there isn't. We can't do a regular substitution here. So we're going to do a trigonometric substitution. First, we identify the case. It's a squared plus x squared. So that means tangent. So my substitution is going to be x is 3 times the tangent of theta. If I make the substitution x equals 3 tangent of theta, then I'm going to have to trade my dx in as well. My dx is going to be 3 times secant squared theta d theta. Doing the same thing with the d theta that we did with the dx in our original integration by substitution. I'm writing dx d theta and then moving the d theta over on the other side. A little bit lazy, a little bit casual. It's fine. It's fine. It works. Let's just be engineers and let it work. So now I got to go in and make my substitutions. I'm going to rewrite this integral as the integral of square root. Haven't done anything with that yet. 9 plus, and then x is being replaced with this 3 tangent theta. And that gets squared. The dx is all this. So you have to multiply by 3 secant squared theta d theta. At least we've made that first step. We have traded our x integral for a theta integral. We have gone into the theta integral. The next step is to simplify our theta integral using a Pythagorean identity. If you start doing trigonometric substitution, you're about to integrate something and you haven't used a Pythagorean identity yet, then something has gone wrong. You're forgetting something. We're going to multiply the stuff under the radical. We're going to multiply out the stuff that 9 plus x squared has become. So this 9 plus the square of 3 tangent theta is 9 plus 9 tangent squared theta. If we factor a 9 out of this, we have 9 times 1 plus tangent squared theta, which is all just 9 secant squared theta. This is the point of the substitution, to take those two terms and pull them down to one term through a Pythagorean identity. This is the point of the process. So our integral now looks like the square roots of 9 secant squared theta. This 9 secant squared theta is from in here, from the quadratic form that triggered this entire process. I suppose I could pull this. I'm just going to leave it there. Once again, the point of doing the trigonometric substitution is pull these two terms into one term with a Pythagorean identity. This is why we are doing this. This is why we made this choice of tangent, why this is the tangent case. Then we can use 1 plus tangent squared and turn that into a secant squared. 2 terms become 1 term. 2 terms enter, 1 term leaves. Integration Thunderdome. No one knows what Thunderdome is. I always refer to Thunderdome, and no one knows what Thunderdome is. Does anybody know what Thunderdome is? One person knows what Thunderdome is? Just one Tina Turner fan? The rest of you need to learn some respect. Now, this is still kind of a mess. I've got the square root of 9 secant squared theta. And I got this 3 secant squared theta. So let's clean this all up. 9 secant squared theta, that's all equal to 3 secant theta. I guess it's a little fishy. Square root of something squared, but it's fine. It's fine. And we got the 2 3s, that'll make a 9. I'm going to pull that out the integral. And what we have is a secant cubed. As advertised, doing the trigonometric substitution has handed us a theta integral that is a product of powers of trig functions, or it's going to be simpler, but a product of powers of trig functions, and it is not going to be substitution. There is not a substitution that's going to be appropriate for this. I can't substitute secant because I don't have tangent. The derivative of secant is secant tangent. So I have one factor of secant to be the dx, the dw, but I don't have a tangent. I can't do a tangent because I need 2 secants, and I only have 1 secant left over that I can't convert to tangents. I need 2 of them to be the dw, and only 1 would be left over. It would end up being a square root, and we'd end up back where we began, with a square root of some shit that we can't deal with. So this is a product of powers of trig functions that is not substitution. So if on your search for products of powers of trig functions that are not substitutions, you came across odd powers of secants without tangents, then you are correct. That's one that is not a substitution. It's parts, but we need to know more to do it. We'll come back to that. We're just learning how to do the substitution, how to get to this theta integral. Any questions? How's everybody okay? Everybody's excited because you can tell that this is going to be the most fun integration. At least that's what I'm pretending. I don't know. So the tangent case was an a squared plus x squared. Note that the tangent case also covers x squared plus a squared. That one can go in both directions. The next one we want to learn is the sine case. This one we have an a squared minus x squared. Remember, we have extra knowledge now. We know the point of the process is to pull 2 terms into 1 term through a Pythagorean identity. And that's why we can tell what case we are in. Because here we have a squared minus x squared. We call it the sine case because we're going to replace a 1 minus sine squared with cosine squared. And 2 terms will become 1 term. Our substitution is a times the sine of theta. If we want to make the substitution a sine theta, x equals a sine theta, then we have to replace dx with a cosine theta d theta. And here we see on display the big difference between the tangent and secant case and the sine case. The derivative of sine is cosine to the first power, just one factor. The derivative of tangent is secant squared, two factors. The derivative of secant is secant tangent. They're different, but there's still two of them. But the derivative of sine, cosine. The other thing that we're going to need is a Pythagorean identity that says 1 minus sine squared is cosine squared. It's right here. 1 minus sine squared is cosine squared. That's how two terms become one term through a Pythagorean identity. Let's look at an example of this one in action. I'm not going to be very clever or creative, but that's only because I'm not very clever or creative. Maybe I should use something more distinctive instead of such a subtle change, but the subtle change is the point, so I'm going to go with just a small subtle change, what we did before. Trading our 9 plus x squared for 9 minus x squared completely changes how we view the problem, because now we see a squared minus x squared. Now we think this is the sine case because 1 minus sine squared is cosine squared. In the previous one, we saw 1 plus tangent squared is secant squared. But in this one, I see 1 minus sine squared is cosine squared. So we'll make our substitution. X equals 3 cosine. I spelled sine wrong. X equals 3 sine theta. If we want to make this substitution, then dx is going to be 3 times cosine theta d theta. Let's make our substitutions. The x gets replaced with 3 sine theta. That's all being squared. And the dx out there needs to be replaced with 3 cosine theta d theta. We have made our substitutions. Now we get to the point of this substitution, which is to take those 2 terms in the radical and turn them into one term. 2 terms enter, 1 term leaves. So we multiply this out, it's always the same. 9, well, barring the signs. 9 minus sine squared theta. Factor out the 9, it's 9 times 1 minus sine squared theta. And 1 minus sine squared is cosine squared theta. Now we find ourselves in the same situation that we were in the previous one with just some different window dressing. 2 terms have become 1 term. In this case, that was convenient because now I have the square root that I can apply to these 2 factors. I can't apply an exponent to terms. Exponents don't distribute over terms, but exponents distribute over products. So I'm going to replace my 9 cosine squared theta with a 3 cosine theta, just like I did before. Only cosine instead of secant. This is all 3 cosine theta. Now, if I combine that with my cosine over here, I can get the 3's together outside. And then I have cosine squared theta to theta. This is our simplified theta integral that we were going for. It is a product of powers of trig functions. That is not substitution. Just like before. Even powers of cosine is not substitution. And in just these 2 examples, we have come across the 2 theta integrals that we're going to need to learn. Odd powers of secant without tangent, even powers of cosine. Once we learn odd powers of secant without tangent and even powers of cosine, the 2 that are not substitution, we have got products of powers trig functions handled finally. But we need these 2. In the case of odd powers of secants without tangent, that's just parts, but it's going to be an iterative parts, and we're not going to like it. Actually, you're not going to like it. I think it's super fun and cool. For even powers of cosines, these can be done by parts, but I don't like doing them by parts because we have trig identities. Anytime trig functions are messing with you, look for trig identities. Trig functions are the fae of the math world. They can make things super complicated, but there's probably some trick. They're all related. There's some trick that if you have this secret knowledge, they will reward you with an easier path. Any questions? Remember the point. 2 terms become 1 term through a Pythagorean identity. 2 terms become 1 term using a Pythagorean identity. The reason that I keep pointing this out is, first of all, it's the point of doing the trigonometric substitution. And second of all, it will help you remember what you want out of your substitution. Secant case has this form, x squared minus a squared. At this point, well, actually, no, this is too new. But at this point, when you think about this later, and at this point, when you start to see the pattern and why the cases are what the cases are, you got to stop memorizing the form and start seeing the purpose. So the form is, when you see x squared minus a squared, this is the substitution that you want to make. When you start to see trigonometric substitution a little clearer, right now it's too muddy and too new. But when you start to see this, I want to point out, you're going to look back at this and say, of course, x squared minus a squared is going to be secant, because I want to use a Pythagorean identity, and I'm going to use secant squared minus 1 equals tangent squared. 2 terms become 1 term. Dx is a times secant theta tangent theta. Because when we're doing a substitution, these integrals have the substitution trait, And one of the things that has to happen when you're doing a substitution, all x must become theta. I've started reading Pathfinder rules recently, and it's much more, it's like 5th edition Dungeons and Dragons, but like with the extra step of having actually been designed to work as a system. It's like 5th edition, but a lot less hand wavy. The other thing that we're going to need is a Pythagorean identity. That's the point of the whole exercise. And we can see the form of what it's going to be. Secant squared theta minus 1 is tangent squared theta. I'm going to stick with this theme partly because it's like the simplest thing you can do, and this is not a substitution integral. So all the same things apply, just copy and paste and then like edit. We identify this as secant case because it's x squared minus a squared. So we make the substitution. X is 3 secant theta. If we're going to make that substitution, then dx is 3 secant theta tangent theta. I haven't noticed anybody using tangent theta secant theta. That's just weird. Like if you're like the derivative of secant is tangent theta secant theta, what? That's like shoe, sock, shoe, sock, shoe, sock, shoe. That's just insane. That's crazy. That's a red flag. If you're like, oh, dx is 3 tangent theta secant theta, I'm like, oh boy, I gotta watch out for this. It's even worse if you're like, oh, dx is sine over cosine squared. And you're like, oh, what the fuck? That's, by the way, one of the prime methods that I use to identify the robot that's been sent back in time to come and murder me. Ah, then dx shall be sine over cosine squared because they come to ox hours. I'm like, oh, it's secant case. Like, ah, yes, x equals 3 secant theta. And what else do you have to do? Then dx will be sine over cosine squared. And then when the secret robot assassin looks up, that's when I have my laser pistol shoot pointed at his face. I'm like, oh, I knew it was you the whole time. He's like, oh, wait. And then I send a message to the future. I take it to this particular field. I put it there so that they'll find the robot assassin's corpse. With a note pinned to his chest. It says, nice try, motherfuckers. I'm just kidding. No one is sending robot assassins from the future to try to murder anymore. They got the message. I'm just kidding. They still try. I'm just kidding. None of that is true. I realize that by saying none of that is true, there are two statements that are exact opposites. And so it's not possible for none of that to be true. I also realized that I just left you with an unresolved set of statements. That pause right there is an indication that I won't be resolving those statements. So here the x is going to be a 3 secant theta. And because substitution, the dx has to go as well, and that will be replaced with 3 secant theta tangent theta d theta. We have made our substitutions. This is our first stop in the theta integral. And then two terms must become one term because that's the point of the process. 3 secant squared theta is going to be from 9 secant squared theta minus 9. Factor out the 9 like we always do. And then secant squared minus 1 is tangent squared. Two terms have become one term through a Pythagorean identity, the point of the process. Now we're at this point, square roots of 9 tangent squared. And the same thing happens that happened in all the other ones because I really have just been doing 3 copies of the same problem all day. This is because I'm lazy and not very creative, but this square root of 9 tangent squared is 3 tangent theta. And then we can just combine all this stuff. I'm going to pull the 3 times 3 out front, and I have secant tangent squared. At this point, you might be looking at this and saying, I thought you said we were going to get a product of powers of trig functions that was either odd powers and secant without tangents or even powers of cosines. And I see some tangents here, but that tangent squared is actually secant squared, because the way to integrate this is to write a secant cubed theta minus a secant of theta, both integrals that we're going to need to know. So we actually, once we're in the land of theta, then we want to get back to at this point, it might seem insane to take one term and break it into 2 terms because the point was to get 2 terms into 1 term. But we wanted to get 2 terms into 1 term because they were sitting inside of an exponent, and I cannot distribute an exponent over terms. I can distribute an exponent over factors. And once we do that, we no longer have an exponent sitting on top of our tangent squared. So now it's a polynomial. It's okay to break it apart. In particular, it's okay to break it apart because that's how we're going to deal with this secant tangent squared. So once again, we're just going to end up with 9 integral of secant cubed theta minus secant theta d theta. So we were looking at odd powers of secants without tangents. One of the things that you want to do when you're looking at this is to make sure that you understand why secant theta tangent squared theta is still not a substitution. Substituting secant doesn't work. Secant tangent is the dw. I'm left with 1 factor of tangent, and I can't fix that. I can't do tangent because I don't have a secant squared. Now you might think if I could write this as sine over cosine squared, robot assassin from the future. Sine over cosine squared doesn't help either. Any questions? Comments? People? All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day. And thanks for playing. I told you this was going to be the most fun one, right? And obviously, everybody's like, oh man, I can't wait for more of this.